In this class, we discuss about the general solution of two-dimensional Laplace's equation, and which is given by del 2y by del x2 plus del 2y by del y2. This is equal to 0, where x and y are in 0 to a and 0 to b. And the given boundary condition are u of 0y, this is equal to u of ay, this is equal to 0. Here this is equal to 0 and this is also equal to 0, where 0 less equal to y less equal to b, this is named as 2, and u of x comma b, this is equal to 0 in 0 less equal to x less equal to a, and u of x comma 0, this is equal to fx, 0 less equal to x less equal to a. Okay, and we solve this Laplace's equation using the method of separation of variable. Okay, and this problem is also known as Dirichelet problem in rectangle. Why say it Dirichelet problem in rectangle? Rectangle, because if we draw a rectangle, this is x-axis, this is y-axis. Here it is given that x equal to 0 to a, so this is 0 to a, this is x-axis, and this is 0 to b, so this is 0 to b, this is y equal to b, and this is y equal to 0, this is x equal to 0, and this is x equal to a. And from the boundary condition we know that u of 0 comma y means x equal to 0, then u equal to 0, it is given. Also u of a comma y, that is x equal to a, u equal to also 0, and where y equal to b, then it is given that u equal to also 0, and when y equal to 0, then it is given that u, this is equal to fx. Okay, that is on the three side u, the value of u is 0, and on the side y equal to 0, the value of u is fx. These are the boundary condition in four sides of the rectangle. So this problem is said to be in a rectangle. Okay, now to solve this problem by separation of variable, we first let u x y, this is equal to x of x into y of y. We separate the variable x and y, and this is relation number 4, or this is relation number 4. Now we differentiate partially with respect to x 2 times and with respect to y 2 times. We get u x x, this is x double dash into y, and u y y, this is x into y double dash. Okay, now putting the value of u x x and u y y, here we get x double dash into y plus x into y double dash, this is equal to 0, and this relation gives x double dash by x, this is equal to y double dash by y. Okay, and here we take a negative sign. Then these two ratio or these two fraction are same, let this is equal to mu, we say this is equal to mu. Now clearly we have three cases. Okay, in the first case we let mu, this is equal to 0. In the second case we let mu, this is equal to lambda square, and this is greater than 0. And in the third case mu, this is equal to minus lambda square, and this is negative. Okay, and as on the wave equation and heat equation, we say that for the first two cases, if we take mu equal to 0 and mu equal to lambda square, then the solution are trivial. So here we consider only the case 3 for non-trivial solution. And before going to the third case, we modify the given boundary condition from this relation, and we get this is u 0 comma y, this is equal to u a comma y, this is equal to 0. So putting the value of this, we get x of 0 into y of y, this is equal to x of a into y of y, this is equal to 0. And since y of y we cannot take this is equal to 0, because this is the general value of y for all value of small y. So here we take x of 0, this is equal to 0, and and x of a, this is also equal to 0. Now we name these two relations as the relation number. This is the relation number, this is 5, and we use the relation number 5 in place of relation number 2 as the boundary condition. These two are the boundary condition. Okay. Now from here we get, for the third case, we get x double dash by capital X, this is equal to minus lambda square, and this relation gives x double dash plus lambda square into capital X, this is equal to 0. And clearly this is an ordinary differential equation of second order, also it is linear and homogeneous. So clearly the general solution of this ordinary differential equation is x of x, this is equal to a into cos lambda x plus b into sin lambda x. Okay, because the roots of the auxiliary equation are m, this is equal to plus minus I lambda. Okay, so the general solution is of the form like this. Now we put the boundary condition. We first put x equal to 0, and we get this is a, this is equal to 0, imply a equal to 0, and then x of x becomes a equal to 0, you put here, we get b into sin lambda x, this is, and we put here x equal to a, so x of a, this is equal to b sin lambda a, this is equal to 0, and from this relation we get sin lambda a, this is equal to 0. Otherwise if we take b equal to 0, then we get trivial solution, and we assume the case 3 because to find the non-trivial solution. So we let here b not equal to 0, and this relation gives lambda a, this is equal to n pi, where n be natural number, that is lambda, this is equal to n pi by a. Okay. Now we get the value of lambda as a sequence, because here n belongs to capital N. So we write this value as lambda n pi by a. Okay, and by putting the value of lambda or lambda n here, we get the value of x, and we get the value of x, we write x n x, this is equal to b n sin, the value of lambda n is n pi x by a. Okay, this is the value of x n. Now we putting the value of lambda here and get the relation as y double dash minus y double dash, this is equal to minus lambda square y, and this gives y double dash minus lambda square y, this is equal to 0, and this gives the solution of this relation or this ordinary differential equation is also b, this is y of y, this is equal to c e to the power lambda y plus b e to the power minus lambda y, because the solution of auxiliary equation for this equation is given by plus minus lambda. So these are real and unequal. Hence the general solution like this. Now putting the value of lambda here, we get yn of y. We first write y of y, this is capital Y of y, this is equal to c into e to the power, we put in place of lambda, this is equal to n pi by a. So this is n pi y by a plus d into e to the power minus n pi y by a. Okay. Now we use another condition from here. This is the second boundary condition, and we get here, this is u of x comma b, this is equal to 0. So x of x into y of b, this is equal to 0. Now if we take x of x, this is equal to 0, then clearly u of x comma y, this is equal to 0, and we get the trivial solution. Or otherwise we also say from the last boundary condition 3b, u of x comma 0, this is equal to fx, it is given, and this relation can be written as this is x of x into y of 0, this is equal to f of x. If we take f of x equal to 0, then we put here x of x equal to 0, and then from this relation we get f of x, this is equal to 0. So we say that if we take x of x equal to 0, then this condition is not satisfied. Okay, so we take here y of b equal to 0 and x of x not equal to 0, right? That is x of x not equal to 0 and y of b equal to 0, and we use this condition y of b equal to 0 here, and getting the relation as y of b, this is equal to c into e to the power n pi b by a plus d into e to the power minus n pi b by a. Now from this relation we find the value of c, and the value of c is given by c, this is equal to minus d into e to the power minus n pi b by a by e to the power n pi b by a. Okay, this is the value of c, and by putting the value of c here, that is in the value of y of y, we get the relation as y of y, this is equal to, we write first this term d into, taking common d from both the term, we put the value of c here, so we take common d, and this is e to the power minus n pi y by b, this is the first term, minus here this is e to the power n pi y by a, this is also a, into e to the power minus n pi b by a by e to the power n pi b by a. Okay, now we taking common e to the power n pi b by a from both the term, and we get d by e to the power n pi b by a into e to the power n pi a into b minus y minus e to the power n pi by a into b minus y, we take common in negative sign. Okay, now we multiply numerator and denominator both by 2, and clearly this is the formula of sine hyperbolic theta. Okay, because we know that e to the power theta minus e to the power minus theta by 2, this is equal to sine hyperbolic theta. We use this relation here, and getting the relation as we put total constant, this constant by another constant, this is e into, because whole term is constant, and this is sine hyperbolic n pi by a into b minus y. Okay, we get the value of y of y, and now we put this value as y n y, because here also n was present, so this is like a sequence of solution, and this equation can be written as en, this is also a sequence, sine hyperbolic n pi by a into b minus y. Okay, this is the value of y, and we name this value as relation number. This is relation number. We first name this relation as relation number 6, and this relation as relation number 7. Okay, now from relation number 6 and from relation number 7 we get the value of unxy. Okay, so unxy, this is given by nx into yny, and this is given by, we write first the value of xn, this is bn into sine n pi x by a into en into sine hyperbolic n pi by a into b minus y, right? And we take another constant, this is fn into sine n pi x by a into sine hyperbolic n pi by a into b minus y, where fn, this is equal to en into bn. We let en into bn, this is equal to another constant, this is fn, and this is unxy, and we name this relation as relation number 8, right? Now by using the superposition principle or using the principle of superposition, we get the general solution of uxy, and which is given by uxy, this is equal to summation n equal to 1 to infinity, this is fn into sine n pi x by a into sine hyperbolic n pi by a into b minus y. Okay, this is the general solution of the Laplace's equation, and we name this relation as relation number 9. Now we use the last given condition or last boundary condition, this is relation number 3. We put here y equal to 0 first, then we get u of x comma 0, this is equal to summation n equal to 1 to infinity, and this is fn and sine n pi x by a into, we put here y equal to 0, so we get sine hyperbolic n pi b by a, right? And we get this is equal to f of x. It is given in the relation number 3. Okay, and clearly this relation shows that this is the Fourier series expansion, or this is the Fourier series of f of x, or clearly we say that this is in particular a Fourier sine series, because here only variable is sin n pi x by a, and this is also a constant. Okay, now to find the Fourier coefficient, we use the formula of Fourier sine series or half range Fourier series here, and we get the relation Fn into sine hyperbolic n pi b by a. This term like the Fourier coefficient, and the Fourier coefficient is equal to 2 by the range of x is 0 to a. This is half range series, so 2 by a into integration x equal to 0 to a, right, into fx into sine n pi x by a dx, right, and we get the value of fn. This is equal to 2 by a into sine hyperbolic n pi b by a into integration 0 to a fx into sine n pi x by a dx, right, and we name this relation as relation number 10. Now we find the value of fn from the relation number 10 and putting the value of fn in relation number 9, we get the general solution of the Laplace equation. Okay, here we find the value of fn by integrating this term and putting this value of fn here. That is the relation number 9, and we get the general solution of the Laplace's equation. Okay, this is a long process to find the general solution of Laplace equation or Dirichelet condition or Dirichelet problem in rectangle by method of separation of variable. Okay, thank you for watching.